I'm Professor Rad, and this is Precalc video 3.7, Graphing Sine and Cosine Functions. So far in our conversation about trigonometric functions, we've been referring to them as functions that have an input of an angle and have an output of a ratio, either a ratio that is involving x and y, or x and r, or y and r. So those are our trig functions: sine, cosine, tangent, and so on. So in this video, we're going to move to looking at what those functions look like if we graph them, where the independent axis, or the x-axis, is the angle, and then the y value is going to be our, the ratio that comes out. So the y is going to be our f of theta, if we have, for example, sine of theta. So to help us convert this into a graph on a coordinate plane, I've drawn a unit circle to help us, and I've marked out some important angles with really nice trig values. So for example, if I'm on the x-axis, my x and y value is either a 1 or a 0, right? I have an x value of 1 here and a y value of 0. If I'm on the y-axis, similar thing, I get a value of either 1 or 0, or -1 or 0 on the negative sides. So we're going to use that to help us graph. So you'll notice that I've indexed my horizontal axis here by the quadrant angles in radians. So in other words, here we have 0 radians, pi halves, pi, 3 pi over 2, and then we're back to 2 pi, and we can keep counting as we go around. So we have pi halves, pi, 3 pi over 2, 2 pi, and so on. So that's why when we're graphing a trig function, very often you're going to index your x values in terms of pi or pi halves, maybe pi fourths, depending on the trig function you're going to graph. So what I'm going to do is I'm going to plot the nice points for sine of theta. Yeah, I think that's a good way to start. So let's start out. Oh, golly. So let's start out with this point here. So this point here, we have an angle of 0. So this is going to be my y-intercept for the sine function, since the angle is 0. And on this point has the coordinates of 1, 0. So the sine function corresponds to y on a unit circle, and cosine corresponds to x. So since we're graphing sine right now, we're going to use the y value as the sine value. So because the y value is 0 here, and the angle is 0, when we go to graph it, we'll have the point 0, 0. Then as I move up to this next point here, this point has the coordinates 0, 1. This means that when our angle is pi over 2, oh no, I erased my arrow. When my angle is pi over 2, the sine function is going to give me 1. So when my angle is pi over 2, the sine function is going to give me 1. Then as I move around, I'm going to come to this nice point here. This point has the coordinates -1, 0. So this is an angle of pi, and its corresponding sine is 0. So that when the angle is pi, the sine value is 0. And we're just going to continue. Let's go all the way around the circle. So as I move here, this point has the coordinates 0, -1. So that when the angle is 3 pi over 2, the sine value is -1. So when my angle is 3 pi over 2, the sine value is -1. And then when I come full circle and I return to this point here, now I've gone 2 pi radians, and my y value is back to 0. Now, if I had an infinite whiteboard, we would actually continue this pattern indefinitely. So I'm going to, as I continue around the circle, these points are going to repeat themselves. So the next point is going to be at basically 2.5 pi, 1, and then we'll have 3 pi, 0, this point repeats, and then we'll have 3.5 pi, -1, because this point will repeat, and so on and so on. as we go around the circle repeatedly. We can also observe that pattern if we go in the clockwise direction. So instead of thinking of this angle as, right, this point as happening at 3 pi over 2, I could think of it as happening at negative pi halves, because now I've gone negative pi halves, has a y value of -1. So at negative pi halves, the sine value is -1. When I go to negative pi, my y value is 0. When I go to negative 3 pi over 2, my y value is 1. And when I go to negative 2 pi, my y value is 0. So you can see that these points are repeating as we go through. So the next question is, how do we connect these? So we're going to, so like, for example, are we going to connect these in straight lines like we would with like an absolute value function, right? So the absolute value function had this sort of V shape and it used straight lines. Or are we going to connect it more smooth, more curvy, like a parabola or a polynomial function? What will this look like? So here's how we can think about the y values of this function. So as I move along through the first quadrant, so as my angle moves from 0 to pi halves, notice that these y values are forming sort of like a quarter circle. Well, not sort of, actually a quarter circle. That's what the y values are forming here. So that means as my angle goes from 0 to pi halves, I have to also form that quarter circle with the values I get. So this piece of my unit circle, when I transpose it over to the sine function graph, is going to look like a quarter circle, like that. As I continue around the circle, so as I move from pi halves to pi, I'm continuing as a quarter circle that's coming downwards. It starts at 1 and comes down to 0. So as I move from pi halves to pi, I'm going to start at 1 and come down to 0 as a quarter circle. Then as I move from pi to 3 pi over 2, we're continuing in the circle motion. Although this time we now go from 0 to -1. So I've got my quarter circle going from 0 to -1. And then to finish our circle, we go from 3 pi halves to 2 pi. We're going to go from -1 to 0 along a quarter circle for my y values. So we go from -1 to 0, like that. And then as I go around the unit circle, I'm going to retrace these parts that I already took. So I'm going to start retracing this purple section next. So that arc is going to repeat as I move over in this direction. And then we can repeat this process going backwards. So if I go in the order of my negative angle, now I'm going to be going from 0 to -1. So I'm going from a y value of 0 to -1. Then I go from -1 to 0. So we have from -1 up to 0. Then we have from 0 to 1. So I'm going to curve from 0 to 1. And then we go from 1 to 0. So we're going to curve from 1 to 0. And then again, this pattern is going to continue. So next, as I continue to go around clockwise, I'm going to be retracing the blue section. So I'm going to continue going like that. So our sine function is going to look like this, more or less. Now, depending on how your axes are scaled, these may or may not look like semicircles like they do on my graph here. And that's just because of how I've scaled the x and y axes in relationship to each other. Very often it'll be a little bit more squished. So it'll look something more like that, depending on how your axes are drawn. So just know that when you go to graph these, it may or may not always look like a perfect, semicircle. So we can repeat this process for cosine. I'm going to go through it a little bit faster since we've walked through it with sine. But for cosine, we're going to be graphing same values from a unit circle. But this time, instead of graphing our y values for each of these points, we're going to be graphing the x values for each point. Because on the unit circle, cosine is the x value. So, this one. Here's -1. Forgot to label my vertical axis. There we go. So if I start out at an angle of 0, the x value is 1. So cosine of 0 is 1. At pi over 2, the x value is 0. So at pi over 2, cosine is 0. At pi, we're going to be -1. At 3 pi halves, we're going to be 0. And then when we get back to 2 pi, we're back to 1. And this pattern is going to continue if we go in the clockwise direction as well. So we'll end up going to 0, -1, 0, and 1. So if we want to check that, we have 0, -1, 0, 1. So our pattern's continued. To graph the cosine function, we can follow the same kind of idea. So this time we're using just the x values as a reference, but the x values are still moving in the same kind of way that the y values were. They're moving in a quarter circle. So as I go from 0 to pi halves, my y values, or my x values rather, are moving from 1 to 0. So I'm going to move from 1 to 0 in a sort of quarter circle-y way. Then as I move here, I'm moving from 0 to -1. So the values here are going to go from 0 to -1. And we're just going to keep plotting the connections as our quarter circles. So we go from -1 to 0. So here we are at -1 to 0. And then from 0 back up to 1. So from 0 back up to 1. And then we continue around. So we're into the purple section again over here. So we're going to continue going down like we did here. And we can also graph backwards. So if I go backwards, I'm going to hit the blue section first, and then the green, and then the red, and then the purple, and then the blue again. So there we go. That's going to be our cosine function. Oh no, I dropped my marker. It's okay. It didn't write on the floor or the wall, so it's a good day. All right. So that's going to be our cosine function as we look at the x values rather than the y values on the unit circle. So you can see already a few features happening as we look at our sine and our cosine functions. So for example, we notice that they are periodic. So a periodic function is a function that is going to repeat itself. So a periodic function is a function that's going to repeat itself. So in this case, our sine function, as we go through these y values, after we hit the end of its period, it's going to repeat those same values. And it just is going to continue that indefinitely. Same thing for cosine. And the reason this is happening is because you can march around a circle as many times as you want until you get tired or run out of board space to graph. So these functions are periodic. We also notice they have a limited range. So both of these functions have a range that's going from -1 to 1 for both the sine and the cosine. And that makes sense if we think about our x and y coordinates on the unit circle. So if I'm a value on a unit circle, the largest I can be is 1, because the furthest away from the center of the circle I can be is my radius, which is 1. And the smallest I can be from that center reference is 0. So that's why we're going to be, we have like from 0 to 1 or 0 to -1, since we have negative x values as well. So instead of just kind of throwing out these observations, why don't we give ourselves a space to write them down? So I'm going to erase this unit circle and then write some spots where we can maybe try and find some observations about these two functions. All right, so let's look at some observations we can make about sine and cosine. So we're going to start out by stating the domain and the range, and then we'll talk about the period and the amplitude for these two functions and what those words mean. And then we'll also look at any symmetry that these functions have. So for the domain, both of these functions have a domain of all real numbers, because the domain is going to be the angle in terms of radians. So you can go any angle around a circle, either positive or negative. So the domain for both sine and cosine is going to be all real numbers, or if you prefer an interval notation, -infinity to infinity. Now the range I referenced previously, so the range, we're kind of trapped here in between -1 and 1 for both sine and cosine. So for our range, we're going to go from -1 to 1. And to indicate that we want to include those values, we're going to use square brackets. So that's our domain and range. These are similar concepts that we've been looking at functions all along. Now for some new, I'm not going to edit that out, I'm just going to leave it. So for some potentially new terms, we have our period and our amplitude. So the period is how long before it repeats. Another way to think about the period is to think about it as how long does it take for the function to go through one full cycle of its patterns. So for example, on the sine function, if I start at this point 0, 0, 0, and I move along the sine function, I've come back to 0 at pi, but I haven't gone through every possible aspect of this function yet, right? There's parts where the function goes below the x-axis, below the x-axis. So if I start at pi and I follow the pattern, I'm going to get back to that starting point at 2 pi. That's like when we went all the way around the circle, we hit all the possible y values. So this is our first cycle of sine. So it takes from 0 to 2 pi. So the period for sine is going to be 2 pi. Now, you don't have to go from 0 to 2 pi to see that period happening. For example, if I go from -pi to pi, that's also a distance of 2 pi. And we hit each part of the sine function. Right? So we get to see all of the components of it. And then notice after pi, we're back to green. And that's where we started. So after there, it starts to repeat. So the period in a distance of 2 pi, we saw the full cycle, and then it'll repeat again. The same thing is true for our cosine function. So if I look at, for example, from -pi to pi, we go through the green, the blue, the purple, the red, and then we'll repeat the green, the blue, the purple, the red, and so on. Or if I go backwards, here's the red, the purple, the blue, then the green. So as I move backwards away from there, it will repeat. So the cosine function also has a period of 2 pi, because in a distance from -pi to pi, or in a distance of 2 pi, we see the full range of our cosine function. The symbol that we're going to tend to use for period is going to be t. So we'll say that t equals 2 pi. For the amplitude is the distance from like the grounding center of the function to its extremes. So our amplitude is going to be, if you want to think of it as like half the total height, you can, or you can think of it as like that distance from the middle to the top or bottom. So on the sine function, the amplitude is going to be 1 because the distance from the x-axis to the top is 1. And we have that same measurement here as well. So the amplitude is going to be 1. And then for cosine of theta, same deal. The amplitude is 1. So our distance from the middle to the top, or say from the middle to the bottom, right? That's a distance of 1. To indicate our amplitude, I'm going to do the absolute value of A. Now, we'll see why I'm using absolute value when we get to a later video about sinusoidal functions. But for right now, just bear with me. We're going to use the absolute value of A. That will be 1. Next, we can talk about symmetry of these functions. So if I look at the sine function, it looks like, let's see, it looks like it has symmetry through the origin. So if I have, at this point, positive pi halves 1, so positive pi halves, positive 1. I also have the point negative x, negative y. I have negative pi halves, negative 1. And that's going to be the case for the whole function. So if I have, like here's pi quarters, and that must be root 2 over 2, because remember that sine of pi fourths is root 2 over 2. If I have negative pi fourths, I have negative root 2 over 2. So the sine function is symmetric through the origin. Cosine is not. So if I'm up here at pi halves at positive root 2 over 2, I'm not going to be down here at negative. Okay, so our sine and our cosine function finally have some little divergence here in their properties. So sine of theta is symmetric through the origin. So this is going to mean that sine, let's see, remember we had even and odd functions based off of symmetry. So this means that sine is an odd function. So that means it's odd, which also means that if I have sine of negative theta, that's the same as negative sine of theta. Because remember, if we have an odd function, that means that f of negative x is the same as negative f of x. That's what it means to be an odd function. So now instead of x, we're just using thetas. And instead of f, we're using this function's name sine. So let's see if we can have some similar relationships for cosine. So when I look at cosine, now the symmetry isn't through the origin. The symmetry is over the y-axis, right? If I fold this in half, it's going to match up perfectly with those y values. So cosine is symmetric over y, the y-axis, yeah. So if we're symmetric over the y-axis, that means it's even. And that means that cosine of a negative angle is the same as cosine of the positive angle. So cosine of negative theta is the same as cosine of theta. So let's check that out. Let's say I have cosine of negative 3 pi over 4. So here's negative 3 pi over 4. And that's going to give me a negative root 2 over 2. So let's look at positive 3 pi over 4. Its y value is also a negative root 2 over 2. So we're going to be an even function, and cosine of negative theta is the same as cosine of theta. I realize I'm just standing in front of that, sorry. All right, let's talk about some more properties. All right, so let's look at the x-intercepts of these functions, because that's usually helpful to know. So if I look at the x-intercepts for both of these functions, because they're periodic, they're going to have infinitely many x-intercepts. So that's really different from the functions we've been looking at so far. The functions we've looked at have had, like with polynomials, you know, the biggest you could get is 1 less than your degree. So for sine and cosine, we have infinite x-intercepts. So if I look what's going on here, we have an x-intercept at 0, pi, 2 pi, and then the next one will happen at 3 pi, 4 pi, 5 pi, etc. Or here we have negative pi, negative 2 pi, negative 3 pi, and so on. So one way that we can represent this in general terminology, for sine of theta, we can say that the x, well, really the theta intercepts, I guess, are going to be at k pi 0, where k is an integer. So this fancy looking z is going to represent integers. And integers are positive and negative whole numbers. So we have, think of all your positive and negative whole numbers. 0, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. So just multiply each of those by pi. So 0 pi, 1 pi, 2 pi, 3 pi, minus 1 pi, minus 2 pi, minus 3 pi, and so on. That's where we have these x-intercepts. For cosine of theta, if I look at what's happening at the pi's, I'm not at the x-intercepts. So we're going to have different values for our x-intercepts for cosine. Here we're hitting at pi halves, 3 pi halves. The next one will be 5 pi halves, and then 7 pi halves. And if we move to the left, negative pi halves, negative 3 pi halves, negative 5 pi halves, and so on. So there are a few different ways that you can represent this. The most concise way to write it that I prefer writing it for myself is to write k pi over 2, where k is an odd integer. So the reason I need to specify that k is an odd integer is because if k is even, let's say k is 4. If I do 4 pi over 2, that'll reduce to 2 pi. And at 2 pi, cosine does not have an x-intercept. It only hits at the pi halves, where the denominator doesn't divide the numerator. So 1 pi halves, 3, 5, 7, 9, etc. Another way that you can represent this, that some textbooks like to represent it, is to say 2k plus 1 pi over 2, where k is an integer. So one way to represent odd numbers in general is to say, okay, well, let's make it even. So take a number, multiply it by 2, that'll turn it into an even number, and then throw it off by 1. So you could either add 1, or sometimes you might see minus 1 here. Either way, you want to be 1 away from an even number. So this is going to be, in my classes, this is the terminology and the phrasing that I'm going to be using and that I'm going to be expecting you to use. But if you look in a book or search online, you may see it written this way. Okay, so just another way of explaining the same thing. Now there's one more property that I want to talk about between these two functions. Oh gosh, I'm just dropping everything today, huh? All right, so if I look at my sine and my cosine functions, they almost looked the same, except one's been shifted. Okay? So if I start out with my cosine and I shift it to the right a little bit, so if I take this lump here and I shift it so it happens between 0 and pi, I will get that lump from sine. And then this piece here, that would be shifted over a little bit. So here, that would be where it would shift to. So we can use transformations to write sine of an angle in terms of cosine, or to write cosine in terms of sine. So for example, if I take cosine of my angle, cosine of theta, and I shift it to the right by pi halves, so I subtract pi halves, that will give me sine of theta. So let's try this out. Let's check it and make sure we did that correctly. So I'm going to pick a value for theta, let's say pi halves. So if I do pi halves minus pi halves, I get 0, and cosine of 0 is 1. Sine of pi halves is 1. So we did that right. So that's not a proof, but that's a real quick check. We can do a similar thing for sine. So if I take sine, and this time I shift it to the left by pi halves, so this lump here gets moved to the left, that will correspond to this piece here. So if I take sine of theta and I shift it to the left by pi halves, so if I add pi halves, I'm going to get cosine of theta. So this is one way that we can transform from, say, either sine into cosine or cosine into sine. The downside when we do this is that we're going to change the angle. So as we saw with our like quotient properties and reciprocal identities and things like that, we wanted to have things in terms of the same angle. So we would want like sine theta over cosine theta. We wouldn't want like sine theta over cosine theta plus pi halves or something like that. So this will be helpful in the future for some properties, but right now there's not a real great relationship to the algebra that we were doing. But it's still a nice little relationship between these two graphs that they're just off by pi halves. So that's going to be it for this video on graphing sine and cosine. So I wanted to make sure we took some time to establish these two functions in particular, because that's what everything in the future builds off of, right? So I'm not going to be as careful in constructing the next ones. We're just going to talk briefly about them and then graph them. And then we'll do a similar thing. We'll look at some properties of them. So in our next video, we'll talk about secant and cosecant. We'll look at their graphs, talk about some of their properties, and then we'll talk about tangent and cotangent. So I hope you found this video helpful in graphing sine and cosine. Yeah, and I'm looking forward to see you in the future. In the meantime, have a glorious day. Bye for now.